So a lot of this unit, especially the first couple of days, there's a lot of notation. Eventually we will, I think I talked about this last week, but when we start getting into it, it'll be really important to visualize what's happening, and it's a bit different from just talking about lines. But it's not too hard. Again, computationally, I don't think it's all that tricky. But it's new, and there's a fair bit of new notation. So that's a big part of what we're looking at today. Okay, so we're just talking about equations of lines, though. It's like almost like we're back in grade 9. Kind of come full circle. So in grade 9, when we first start talking about equations of lines, we talk about them in terms of slope and a point typically. And if you have 2 points, you can find the slope between them. But really, the equation of the line is all about slope and a point. So there's y equals mx plus b, where m is the slope and b is the y-intercept. There's y minus y1 equals m times x minus x1. We usually think of that as the formula that we use to find the equation of a line, but I could plug a point in and the slope and leave it like that, and it would be still the equation of a line, just not in a simplified form. So y plus 3 equals 1/2 x minus 5, right? Like that's the equation of a line. And then there's standard form. Standard form is not typically useful. What's the point of it? Well, we like the fully simplified form of things that has no fractions in it. That's one reason. When we extend from straight lines, degree 1, into degree 2 and degree 3 and so on and so forth, all the other polynomials, we have that same kind of fully simplified, fully expanded version of an equation, right? So it's sort of similar to that. Anyway, those are kind of what we looked at in terms of lines in the past. So why do we introduce a new notation? Well, as you can imagine, there's different things that you can do when you're working with vectors that you can't do it in the same way. There's some nice things about how we represent lines this way, but then in particular, when we start talking about planes, it adds a lot of value to have this new notation. Okay, so the first part here, there's two things to consider when we are defining a line with vectors. Similar to slope and a point, we have a position vector and a direction vector. So the direction vector you could think of kind of like the slope. It's very similar, and the position vector is very much like a point, but it's all in vector notation, and it all has to do with vectors. So let's take a look at this line. We're going to graph it. In this unit, absolutely being able to graph lines easily and think about their properties is going to be pretty important, right? Like this is supposed to be a no-brainer for us graphing this line. So it starts at 4 and up 1 over 2, up 1 over 2. Whoops. Up 1 over 2. All right, got that? So we could pick any point we want on this line, I'm going to pick this one. Two, 5. So this gives us the position vector. To 5, and make sure that when you're doing a vector that you use square brackets, because that, again, that's a notation, and that's really important. You'll start to see, I suppose in the last unit we didn't probably have to worry about it as much, although it's still notationally like you do have to, but we got away with it if we used round brackets for vectors because we didn't talk a lot about points. But in this unit, we're going to really have to distinguish between, is this a point or is this a vector? There's a big difference between those two things, even though in a lot of cases there's a relationship between them. So make sure that you're using square brackets when you're talking about vectors. For the direction of the line, okay, we need a vector that's parallel, but it's going to have its tail at 0, 0, so that we can define it as a proper vector. So again, this is why I say it's very much like the slope, and the slope was a half, so up 1 over 2. So if I start at 0 and I go up 1 over 2, then my direction vector, which we often denote as vector D, is 2, 1. That's parallel to our line. And this gives us the equation two 5 plus t times 2, 1. So that's the vector form of the equation of a straight line. So t is a scalar. And if you think about it, this equation makes a lot of sense. And you see why any point would work, because I can make t anything I want. If I make it 2, I'm going to start at that point, and every time I go over 2, I'm going to go up 1, right? So I'll go over 4 up 2, like if I make t 2, right? So I can scale the direction vector as big or as small as I want, multiply it by fractions, decimals, whatever you want, and you can see how that's going to give us all the points on the line. Okay, and then there's our little summary of that. So x0, y0 is a position vector, and m1, m2 is the direction vector. T can be anything. There we go. Our first little bit of new notation. Seems pretty straightforward so far, I think. Everybody okay? So we got 2 points, 3, -2, and -1, 5. I think we should probably graph them. Okay, so we're going to, and then come up with the equation. So I can pick any point on the line, but I'm going to use one of the two given points just because. And I'm going to let the position vector be point P. And the direction vector will be PQ. Remember how we find PQ? Okay. So -1 minus 3 and 5 minus -2. And then our equation is just going to be like that, right? Any questions about that so far? So my direction vector is -4, 7. Where's that? Right about here. Parallel. Okay, so I've got P. This was point P here, this was point Q. So if I think about those two vectors individually, and then vector PQ was the one that I found the direction vector for, and it makes a closed triangle, which you can think of as how we found the equation of that line. I think it's pretty straightforward. Everybody okay so far? Okay, so we can do all the same kinds of things with equations of lines that we've done in the past, like determine if a point is on the line. So if I think about my equation, so the x value -4 will equal 3 plus t times -4, so minus -4t. I'm just taking the x components. And 10 is -2 plus 7t. You see where that came from? Okay, and I'm going to solve these for t. And what do we get? What do you notice? What do you think about that? Think about what t is. What do you think? Anybody? Huh? Yeah. Okay, so if I make t2, then I'm going to find another point on the line when I plug that into the equation. Right? It's going to have the same impact on both the x and the y, and it'll be a point on the line. These are different t values. So the way I got x was different from how I got y. So if they're inconsistent, that means the point's not on the line. So since t is inconsistent, this point, -410, is not on the line. So can we find a point that is on the line? We can just say, I don't know, t equals -1, pi, 10, whatever you want. Easy enough, right? A little bit different from plugging in an x and getting a y, but it's not hard to do. Okay, so that's one of the forms. That's one of the sort of new notations. This one's not too different, but like it's related, certainly. But again, this is why I said there's a lot of notation because there's a few different ways that we might talk about and represent equations. Okay, so parametric equations are when I split up the components and I would do something like this. Line 1, and I do it in two parts. So x equals, it might be 5 plus 2t, and y might be -3 minus t or something like that. Okay, so we write it this way as separate parts called parametric equations. This is a very common notation. You don't see it till the very end of high school, but it's like a notation that some people might use exclusively. And if you were taking math next year, you might end up in courses where you do a lot of this. Okay, so there we go. There's an example. Given the parametric equation of the line, write a vector equation, find two other points on the line. So this is like just getting used to the notation and going back and forth, you're going to notice that all of these questions are asking us to go back and forth between all the different kinds of notations, including we will sometimes look at the grade 9 notations, the ones that we're familiar with, we'll compare it to those, and just doing, again, the same kinds of things we've done in the past, finding points, comparing different lines to each other, and that's just to get used to the notation. That's all. Okay? So, write the vector equation of the line. You can go ahead and try it if you want. This should, usually we don't say L1 equals, we use like a colon. You'll notice these are both apparently not done right. Okay, so we can see how they're related. If I compare this to the definition of a vector form of an equation, you can see, and it's kind of obvious, kind of intuitive, I think. Find two other points on the line. So maybe t equals 3, t equals 4. Try that. Oops. Yeah. I don't think you have to. It does say points and those are vectors, but I think in this case it's fine to leave our answer like that. If you were, that being said, technically I suppose maybe we should, and if you were doing something with it as if it was a point, then certainly you would write it with round brackets. Determine if this line is parallel, perpendicular, or neither. How are we going to do that? What part of the equation has to do with its slope? This is the direction vector, right? So we want the direction vector of both. So the direction vector of the first one is 3, 5. And the direction vector of the second one is negative 5, 3. I could put it in to vector form to see that, but you can see where that comes from, right? The coefficients of the t terms. What would be true if they were parallel? They'd be the same, or, yeah, or if they're like an inverse of each other, something different's going to happen. Like when we talk about the slope of a line, if I have a slope of 1/2 or if I have a slope of 2/4, but we don't write fractions like this because it's not fully reduced, but they'd be the same. But direction vectors might not be fully reduced, right? We don't think of it necessarily the same way. You could certainly do that if you were creating the equation of a line, make sure that it was reduced. So really what we're looking for is a k value, but in this case there isn't one, where d1 would be equal to k times d2. So if one is a scalar multiple of the other, then they're parallel. The idea of like similar, to a fully reduced fraction. But if you're looking at them carefully, you might notice something about them. They're certainly... What if I take their dot product? So that's going to be 3, times negative 5 plus 5 times 3. Negative 15 and positive 15 to 0. And if the dot product is 0, yeah. The direction vectors are perpendicular and the lines are perpendicular. Or orthogonal, depending on what language we're using. I know, pretty straightforward so far. What about the equation of L1 in standard form? So again, this is what I mean, like we do kind of, it's helpful to be able to switch between all the different forms, the ones that we're used to from the past and the ones that the new ones that we're learning. We've got 2 points. So I can find the slope between those 2 points. My 2 points were 7, 19, and 10, 24. So y2 minus y1, that's 24 minus 19 over 10 minus 7. So my slope is 5 over 3, and I pick one of those points. Multiply by 3 on the left side, and multiply by 5 on the right side. And standard form, we usually like to keep the x positive, but it doesn't really matter. And add 72, so I get 22 equals 0. No fractions, everything grouped on the same side. Everybody still okay? Whoops, these should be capitals. by plus c see, again, there's a lot of definitional, a lot of notation stuff happening. So we call that a scalar equation. When we are talking about like vector notation and that kind of thing, we would call this the scalar equation or scalar form of the equation. And when you're in scalar form, there's your direction vector, negative b comma a. Again, if you rearrange that in the slope form, you could kind of see where that's happening. And turns out the normal, we talked about the normal back in calculus, okay? And it seemed like just something that we did, like it was just a question that would give us something a little bit different to do when we were talking about equations of curves. But it turns out that the normal is really important when we're talking about lines and planes. So if I have the scalar equation of line L, then the normal would be positive A, positive B. And that can be useful. Any questions? Getting close to the end here. Okay, so we're given a scalar equation. What's the direction vector? Looking back, it's negative BA. So negative 5, 2. And the normal vector is 2, 5. We just did that. We just talked about a line that's perpendicular and saw like the dot product, right? So you can see why that would be a normal vector to the line. Write a vector equation of the line, write parametric equations of the line. You can go ahead and start those. For vector equation, what do we need? That was the very first thing that we did. We need a position vector and the direction vector. We already have the direction vector, position vector. In other words, a point on the line. So you got to figure out a point. How are you going to do that? I would just kind of inspect it and think about it. If I put 2 in for x, I get 2 times 2 is 4, and 1 in for y, 5 times 1, so I get 4 plus 5 is 9, minus 9 is 0. So 2, 1. Gives me 0, which is equal to the right side. So I've got position vector. But again, you could use any point, right? We've got our direction vector from above. Oops. Parametric equations. Question E, solve each of the parametric equations for t. Okay, let's do that. So I start with x equals 2 minus 5t. Bring the x over, and I get x minus 2 equals negative 5t. X minus 2 over negative 5 equals t. Y minus 1 over 2. So now I've got two equations for t. So if they're both equal to t, I can set them equal to each other. And this is called the symmetric equations of a line. So three new kinds of equations, three new forms of an equation today. So I mean there's a lot of notation. This one, if I could rearrange it, it would be like a scalar equation, same idea. Okay. All right, last thing, I'm going to let you give this a try. What's different about this one? Oh, it's in 3 space. And so if you start to think about this line that connects these 2 points, you can start to see where this unit is going. Because imagine 2 lines in 3 space. Are they parallel? Are they perpendicular? Do they cross each other? 2 lines in 3 space don't have to be parallel to not cross each other, right? Because they could go like this. So things get a lot more complicated in 3 space when we talk about equations of lines and different lines and comparing them. And then we introduce planes, and you can have a line that passes through a plane or is orthogonal to the plane, or all different kinds of things. Okay, so that lots of stuff starts to happen. Okay, so go ahead and try to write the vector equation. It's the same in 3 space as in 2 space. You need a position vector and a direction vector. Don't just copy me, you do it yourself. Whoops. Parametric equation. And symmetric equation. X minus XO, so it's X plus 3 over 5. Y minus 0, which is just Y over negative 1, which is just negative Y, but I'm going to write it like that anyway. Z minus 1 over 2. And last question, determine if this point is on the line. How are we going to do that? Again, maybe in here is where we start to see why we need, or why it's can be useful to have a different form. Because if I'm talking 3 space, like when we were doing in grade 9 when you did equations of lines, you just have input, x, output. X is your input, y is your output. That's how we think about it. But we don't really have that anymore. We've got 3 values. So I can't just plug one in and solve for the other 2. Like that wouldn't really make any sense, right? So we're going to see if I get the same t value for each of them. So negative 0.5 plus 3 over 5, which is 2.5 over 5, which is 0.5. So the first 2 are good. But the Z didn't work. So it's not on the line. I think if Z was 2, would that work? So 2 minus 1 would be 1. 1 over 2 is 0.5. So yeah. So if Z was 2, that would be a